This lesson is for Mrs. Cucci's College Now Pre-Calculus class. We are on lesson 4.6, Applications and Models, Growth and Decay, and Compound Interest. So go ahead and open up the document on your calculator and we'll get started. Okay, so by the end of this lesson, you will be able to solve applied problems involving exponential growth and decay, solve applied problems involving compound interest, and find models involving exponential functions and log functions. This lesson is actually really important because this is all of the stuff that we've spent the entire unit talking about, exponential functions and log functions, but this is why we talk about these things. This is where it gets used in the real world, and it does have a great importance. Okay, so let's first talk about population growth. So population growth, we can use the function p of t equals p sub o times e raised to the kt, where k is greater than 0. This models many kinds of population growth, whether it be a population of people, bacteria, cell phones, or money. All right, so your p sub o is going to be your initial population, or your population at time 0. Your p is your population after time t, so what we wind up with. And k is known as the exponential growth rate. So you're going to need to know those variables and what they mean in order to successfully use this formula. Okay, so let's look at this first problem here. I've got the population growth of Mexico. So in 2011, the population of Mexico was about 113.7 million people. And the exponential growth rate was about 1.1% per year. So what we're going to do is we're going to find the exponential growth function. We're going to graph that function and then estimate the population in 2015. We're also going to determine after how long the population will double what was in 2011. So when will it be double this value here? So there's quite a bit that we're going to actually do with this problem. So first parts first, we're going to go ahead and we're going to find the exponential growth function. So we have to think about all of our important information. So let's pull out what we know. We know that the initial population, or p sub o, is 113.7 million people. Okay? So that's one of our knowns. And we know that was in year 2011. Okay? We also know that our growth rate, a growth rate which we call K, was 1.1%. So that's our growth rate. So we need to be able to pull out all that important information. Okay, so since that's what we know, we can go ahead and take the formula, which was P of t equals p sub o times e raised to the kt, and we're going to substitute directly into there. So p of t equals p sub o, 113.7, times e raised to the k, which was 1.1. And if we remember when we were talking about exponential functions prior, we know we don't put things in as a percentage, we put it in as a decimal. So we're going to go ahead and change this to a decimal by moving the decimal 2 places to the left. So 0.011 times t. Okay. So this is our exponential growth function that we're going to use to determine the rest of these problems. Okay, so our next part was to graph. So we're going to go ahead and use our graphing calculator for this. We're actually graphing this equation here. Okay. So I'm going to add in my graphs page. And we're going to graph that function, 113.7 times e to the 0.011. And we do have to use x because it's in terms of f of x. Okay, and we're going to hit enter. Now our graph doesn't show up, and that should make sense because 113.7 is quite a bit larger than 6.67. So we do have to adjust that window. So menu, window settings. My x minimum, since we're talking in terms of time, time is our domain. We don't need negative time. We're going to start that as 0. And let's say this is 80. We're talking about years here. So 80 years is a pretty good stretch of time. My minimum y value, we'll make that 0. And my maximum, let's say 300. And that's just kind of like a guesstimate. Well, that gave us a pretty nice function. All right, so there's our graph. Okay, so part C wants us to estimate the population in 2015. In 2015, we have to think about how our time works. Our x-axis goes by 1. Okay, t is our time, and time is not spelled with an A. Good job, Mrs. Cucci. Okay, make that an I. Okay, time is t, and we know that this is along our x-axis, right? So we're saying that when t equaled 0, the year was 2011. Okay, so if I'm talking about 2015, if I want to estimate the population in 2015, that means t is going to have to be 4. 2012 would be 1, 2013 would be 2, so on and so forth. Okay, so you have to make sure you adjust for that. We're not going to put in 2015. That's going to give us an outrageous value. So you have to make sure you read carefully and see how we're using the function itself. Okay, so in order to determine or estimate the population in 2015, we're going to take that t and we're going to evaluate the function at 4. Okay. Well, we could put that right into our calculator to evaluate it. And we get approximately 118.8. Now remember, that's talking in millions. Another way we can actually look at this is, since we do have this graph, is I could pull up this table and look at x equals 4. My y value there is 118.8. So we can do it graphically, we can do it algebraically. Either way, we get the same thing. Okay, so part D says, after how long will the population be doubled to that of 2011? So if we're doubling the population, that means we're doubling my initial value. Doubling means to multiply by 2. So 227.4. Okay? So what I can do is, that's my P of t. That's what I want my population to be. So I can actually set this equation equal to 227.4. And I want to know in what year. So what I'm solving for here is t. Now I could do this algebraically, I could do it graphically. We're going to take a peek at how to do it both ways, but you do need to know how to do it algebraically. And we did this in the last 2 lessons ago. We were solving exponential equations. So again, the goal is to get the exponential piece by itself, so that 113.7 needs to go away. We need to bring that to the other side, and we're going to do so by dividing. Okay. So when I divide that over, that's pretty simple. Since I know I doubled it, it's going to be 2. Okay. So now, since I'm dealing with an exponential equation with a base of e, Remember that we use the natural log, so that's the inverse. So I get ln of 2 equals 0.001 t. Then one last step to solve for that t, and we're going to divide. And we get t to be approximately 63. Okay, so the population of Mexico will be doubled that of which it was in 2011, approximately 63 years after 2011. Okay, so 63 years after 2011, the population will be doubled. Okay. All right, so let's talk about interest compounded continuously, and you've seen this formula before. P of t equals P sub O times e raised to the kt. I think you guys saw it as A per in 11th grade. Okay, so interest compounded continuously. Suppose that $2,000 is invested at an interest rate of K, compounded continuously, and it grows to be $2,504.65 in 5 years. A, what is the interest rate? B, find the exponential growth function. C, what will the balance be after 10 years? And D, how long will it take the 2,000 to double? Okay. Again, this is all stuff that's pertinent to your lives. This is information that you should know when you're talking about your own financial well-being. Okay? All right, so let's talk about what we know. We know that our initial amount is $2,000. Okay? So when the time equals 0, we have $2,000. Great. We know that eventually, after 5 years, we're going to have $2,504.65. But again, that's after 5 years. So that's your P of t, not your P sub O. Okay? So that first problem wanted us to figure out what the interest rate is. So we have to take what we know. So we know we can start our function at 2,000, E times KT. We're looking for that K for part A. So the only other piece of information we have is that P of t after 5 years, so that's what we're going to have to use. We're going to plug that in. And we know at that time would have to be 5 in order to get that $2,504.65. So now we're going to go ahead and solve for K. So we want to get that exponential piece alone. We're going to do so by dividing both sides by 2,000. And once we do that, we're going to take the natural log of both sides. Okay. So one last step here, and that's to go ahead and divide K by 5. Maybe that's a little messy. I better break that up another step for us. Whoops, hello. Okay, so now divide by 5. And we could take that really big, ugly function right here. We could just pop that into our calculator and find the value. So we're going to find K to be approximately 0.045. So the interest rate is going to be, move your decimal 2 places, 4.5%. Okay, so you always want to bring that back to a percentage. All right, so now by finding that interest rate, it allows us to build that exponential function so that we can actually see that growth function. All right, so let's think about again what we know. We're going to say P of T equals $2,000 times E raised to the K, which is our interest rate, right? 4.5 T. So there's our exponential growth function. All right, so part C wanted to know the amount after 10 years. So we've got our function here. All we need to do is evaluate it at 10. And again, you're going to simply place that right into your calculator. And you're going to find that value to be approximately 3,136.62 cents. Okay? All right. So the last part wanted to know how long it would take in order to double our money. Okay? So if we're talking about doubling our money, if we're starting with 2,000, that means we want to end up with 4,000. So that's going to be our P of T. And since we're wondering how long, what we're looking for is T. So again, it's another exponential function. So we're going to go ahead and solve this out. So we want to get the exponential piece alone. Divide by 2,000. And since I doubled it, I know it's 2. Since the exponential function has a base of e, we're going to go ahead and use natural logs again. Ln of e is 1, so that's why I get rid of that. Okay. Last step is divide by that 4.5. And we get t to be approximately, when I place this into my calculator, I put in the wrong value, 0.045, 15.4. Okay. So, where'd I get that 0.045 from? Some of you are wondering, right? Here's where. Remember, I do not put this in as the percent. What do I put it in as? I have to put it in as the decimal, 0.045. Okay. If you're going to put it in as the percent, you have to use the percent sign in your calculator. We're not going to do that. I'm in trouble for that one. Okay? Putting myself in timeout for that one. I think maybe 9 o'clock at night is too late to be making pre-calc videos. Okay, so again, please, please, please make sure that you put the rate in as a decimal. And I'm pretty sure that I specified that earlier in the video. Look at, I even did it for myself right here. Oh, goodness gracious. Okay, so please, again, make sure that that's written as a decimal, not as a percentage. And I am done making videos for the evening. All right, guys, come and prepared with questions. If you need me to go back over Part D or Part C, I understand. And I will see you in the morning. All right, guys, bye.